Hello, everyone, and welcome to another online Causal Inference seminar. Today, we are happy to have Rodrigo Pinto from UCLA talking about what is causality, how to express it, and why it matters. After Rodrigo's talk, we will have Ilya Shpitser from Johns Hopkins as our discussant. And yeah, let me hand it to Ying for handling the Q&A and moderating it.
Thank you, Razi. As usual, please use the Q&A section to submit your question. And we encourage you to submit your question as soon as you have them, instead of waiting for us to ask you for questions. And please do submit through Q&A instead of chat for us to better track the questions. And without further ado, please feel free to go ahead, Rodrigo.
Well, thank you very much. Thank you very much for this opportunity. So today I'm going to talk about a couple of papers that I published with Heckman on causality. Well, the papers are quite long and have many topics of causality. So in these 45 minutes, I tried to select some topics that might be of general interest. And the title of my presentation is What is Cause Effect, How to Express, and Why it Matters. Well, in summary, the concept of causality is quite well understood. It's an old concept. And traditional economists have studied causality by using structural equations and some causal tools to do causal inference. But these methods are not unique, and you have some other types of frameworks that also use causality. So the idea was to contrast different types of causal frameworks and discuss a little bit of their advantages and drawbacks. So part of this presentation is pretty much going over some basic concepts of causality and gives some perspective of how to compare these methods. And hopefully at the end, I'm going to talk about some new approach that might be new for some of the audience. I'm especially going to talk about what I call the hypothetical model. It's a model that's kind of based on Habermas' idea on causality, the language of potential framework, the Rubin that everyone knows, and also the do calculus of Pearl. And for this talk, I'm going to spend some time, not much, on fundamental concepts of causality and talk a little bit of causality in my field in economics. And then I'm going to go over some counterfactual methods in which I'm going to show a little bit of three different methods and how different ways to think about counterfactuals can change quite dramatically how you're going to, the tools that you're going to use to do causal framework. Then I'm going to talk about the benefits and the drawbacks of the language of potential outcomes, which is the method that's most used by economics. And then at the end, I'm going to talk a little bit more on methods such as the do calculus that study more complex causal models. So fundamental concepts of causality. Preach had this quote on what will become the concept of causality that's quite revealing. It says that causality is not actually a description of an actual word, but much more an exercise of abstract thinking in which you manipulate abstractly inputs, cause, and outputs using the hypothetical variation of these inputs to examine causality. Habermas, other important economists that have studied causality, go further, and he established that to understand causal effect, you actually have to use this thought process, because causal effects are not a description of actual words, but description of these hypothetical scenarios in which you do this hypothetical manipulation of inputs that affects outputs. And pretty much what I'm going to do in what I call hypothetical model is a simple formalization of these ideas. Now, just to introduce causality and put everyone on the same page, I start here with a simple model in which y is caused by t and u, and I'm going to use linearity. Y is equal to alpha plus beta t plus u, and I'm going to define the counterfactual as this causal operation that fixes the input t that causes y to to a value little t. So my counterfactual outcome yt is going to be alpha plus beta t plus u. And then if you'd like to get the average causal effect of one increasing unit is t, you're just going to get the expected value of yt plus 1 minus yt. And for sure, you're going to get that the causal effect is going to be equal to beta. And that is, well, very simple analysis of causality. The key feature here is that we are actually kind of fixing t, the variable t, to a value little t. Now, just to contrast causality with statistical operation of conditional expectation, suppose that we get that the mean of my unobserved variable u is equal to 0, then the expected value of my counterfactor is going to be alpha plus beta t. And if I go outside the world of causality and actually in the world of statistics, I can assume that the expected value of u conditional t is equal to 0, that the conditional expectation of y for t equal to little t is going to be exactly the same expression that we had before. And these expressions are mathematically the same, but they are actually drawn on very different concepts.
Hi, Rodrigo.
Yes.
Sorry for interrupt. Just to bring up a very quick clarification question. Can t be a continuous variable or only a binary treatment?
No, t can be a continuous variable.
Okay,
it can be
thank
whatever
you.
you want. And
Thank
the key feature that I would like to stress here, that the concept of causality is extremely simple. It's just that you have kind of you define a causal direction in which y is caused by t and u. And the concept of causality is simply the hypothetical manipulation of one of its inputs.
Thank you.
And in this little example, I'm conflating two concepts. One is the counterfactual mean of the outcome y that is generated by fixing the variable t to value little t, while the other one is simply the conditional expectation. Again, these two operations have the same mathematical formula. They're mathematically identical, but they're quite distinct in terms of its nature. In terms of the counterfactual mean, the counterfactual mean is a causal statement. It's derived by fixing the variable t to a value. So I'm hypothetically assigning a value little t to an input that actually caused the outcome y. And in this setup, I need more information than simply the statistical operation of compute the conditional mean. Why? Because I require the knowledge, or at least the assumption, that is actually a t that's actually causing y. In the case of the conditional mean, it's simply an operation that uses the joint distribution of both the variables y and variable t. I could also compute the expected value of t condition on y. That's such a valid statement. And in the statistics, you do not have this notion of direction, because in both cases, compute the expected value of y condition t or vice versa, you simply use the joint distribution of the variables, and you're not inputting the information that one variable causes another. So in that case, I'm not using the sense of direction. So although they have the same equation, the nature of these two parameters is quite different. Indeed, when I was kind of started studying causality back in my beginning of my PhD, I found it really, really confusing, especially kind of reading the papers of how people manipulate causality in policy evaluations. And the key feature is that often papers try to use statistics to convey concepts of causality, but causality is something that first it needs more information than study the probability of statistical analysis, because it uses this concept of directional causation between the variables, while statistical models usually do not have directionality. It's just based on the joint distribution of the variables. And you need this concept of fixing. And fixing is this causal operation that assigns values to inputs or arguments of structural equations that cause some outcomes. And this fixing operation is not a well-defined concept statistically. It actually belongs to the realm of causality. Now one one reason for sort of quite amount of confusion regarding causality, especially in economics, but I believe in other fields, is that the causality is often introduced and discussed using econometric models. Usually the simplest one, which is the least square regression, the ordinary least square. And the ordinary least square, it's a model that is based on, it's defined using statistical assumptions. And these statistical assumptions, they do not use concepts such as fixing or counterfactual, or do not even introduce the concept of directionality and causality, but they are based on statistical assumptions that lack this causal interpretation. And this thing causes a lot of confusion. One of the main confusions, in my opinion, is that introducing causality using an econometric model that is defined by statistical assumptions is that it reverses the natural logic of how to think about the causal methods. Because in causality, ideally, you first would define a causal model in which you define the causal directions in which one variable affects other. After that, you would study the identification of causal parameters that you're going to define based on this causal, based on the counterfactors. And after that, you're going to apply an estimation method that you're going to estimate these causal parameters. But when we start studying causality, already using an econometric model that is an estimator, then you reverse this logic of causality because you already started with a procedure that is meant to estimate a parameter instead of actually following the natural steps of how to study causality. I'm going to use three very simple linear models here just to try to illustrate what I'm talking about. All these three models are based on the same outcome equation, y is equal to alpha plus beta plus t plus u. And the only difference that I propose this model here is that I'm changing the causal link between the variables t and u. The error terms epsilon t and epsilon u are exogenous variables. And in the first model here, tu are exogenous themselves, so they do not cause each other. And in this case here, t statistically independent of u. And because of that, the least square regression is going to produce an estimate that's unbiased. It is indeed has this interpretation, the previous interpretation that we have, that it is the causal effect of t on y. But suppose that I create a correlation between t and u, and the correlation is that u causes t. And when u causes t, then t and u are not statistically independent anymore. The parameter beta that's estimated by least square regression is biased. However, the beta still has the interpretation of the causal effect of t on y. But if I reverse the causal link between t and u, then I still lose the statistical dependence between t and u, so the parameter beta is going to be biased. However, the parameter beta loses the causal interpretation that it has before. The parameter beta is not the causal effect of t and y anymore, because now t also causes u, so the effect of t is divided into the direct effect of t and y, which is given by beta, but the indirect effect of t and y that's through u. But in terms of statistical assumptions, pretty much of this model 2 and model 3 are statistically described in the same manner. Just as that's a linear model in which the observed treatment t correlates with the unobserved error term u. So you do not have the possibility to actually change the interpretation of the parameter beta, because statistical models do not have this ability to actually define the causal link between the variables t and u. So it indeed it's just kind of a way to say that it's interesting to actually study causality in a different realm than statistical models and have this knowledge of causality, ideally before studying estimation methods. Now, what is the traditional approach that econometricians, economists have taken to study causality? Tradition, and by this I mean kind of since since cold foundation EA and so on, the standard method is to employ structure equations that describe causal models. And then after that, we define counterfactors using this fixing operation. And it was often the case that it traditionally would disentangle the identification of cause effects from estimation. Indeed, you have often a single type of identification assumption, and you have a range of type of estimations procedures. So you disentangle these two tasks. And sound method for you to organize the construction of the model and how you implement policy evaluation would be to first define the causal models. And the causal models are assumptions among causal links within the causal relation between the variables. This is based on scientific theory, in my case, in economic theory. And then after having a causal method, you define your causal parameters. And to the causal parameters, you're going to use, well, pretty much mathematical analysis, and you're going to use some of the tools that we're describing here. And after defining this parameter, then you go to the estimation methods. But this logical sequence of tasks, it's often blurred, especially in economic papers. Because it's often the case that in economic papers, the authors start with the regression or the statistical method that he's using to estimate some parameter. And after that, he adds assumptions that assign causality to the parameter that he estimates because of the method. So through the years, the goal, I would say, the primary objective of analysis of policy evaluation or empirical exercise become the regression or the econometric method that the person is actually using, and not the causal links or the causal model that is there. And that's often one great example of this would be the methods such as diff and diff we were talking before the presentation, which is started as an empirical method, and it has a notion or a feeling that it captures some type of cause effect, but it was defined as a statistical method to estimate parameters. And only later on, indeed, kind of more recently, many economists have studied diff and diff in detail and create a causal framework that actually assigns causality to the parameters investigated by diff and diff. And the revolution that it has, the method was quite interesting because then it shows that lots of the estimations that people have been doing has a very complicated causal interpretation of the parameter. So let's start with actually the causal model. So what will become the standard causal model in a very general setup? It is a simple framework that has three components. It has random variables. It's just kind of a set of random variables. In these random variables, especially in economics, there are both observed and unobserved random variables. And sometimes the unobserved random variables are very, very important for the economic analysis. For each one of the random variables, you have an error term. And to connect those two, you have structure equations. For each random variable, you have a structure equation that maps what are the inputs associated with the random variable, so it determines the causal link between those random variables. So in that setup, the model is purely non-parametric. And with this setup alone, if you have error terms that is statistically independent, and if your model is non-recursive, you can use Bayesian networks, which are methods that translate this causal relation between the variables into conditions statistical independence. Very important ones are local market conditions, as the variable is independent of its non-descendants, conditions its parents. And you also have graphite axioms that translate some independence condition of variables into others. In particular, the contraction intersection are those that I myself don't use a lot. So what would be defined? How to define a causal model? And for here, I'm using the IV model, instrumental variable model that is widely used in economics. So in this model here, I have an instrumental variable z, that is an external or exogenous variable, is only a function of the error term. You have an unobserved variable v. This unobserved variable v, I use a circle just to show that it's not observed, and it's an unobserved variable v jointly cause t and y, which makes t endogenous. And here are three representations of the same model. They're equivalent. In one I use structure equations, the other one I use the DAG representation, direct acyclic graphs, and the third one I use local Markov conditions. What is fixed in this model here? Well, I intend to examine the cause effect of t on y. So the counterfactual outcome is defined as yt, which I use the structure equation, the function at y that I do not observe, or I do not assume any functional form of y, and I fix the input of t to the value of little t, v, and epsilon e. These are the other arguments of the function. Now, again, fix is not static condition because fixing does not modify the distribution of the variables that are not affected by t itself. So the distribution of z and v stay the same. While if I were to condition this data on t, I would necessarily change the distribution of z and v. So fixing capitalizes indeed outside the probability theory, and there are several frameworks that devise methods for us to cope with this lack of tools that standard statistical probability theory has regarding the fixing operator. Now I'm going to talk about some counterfactual approaches that use it to manipulate this operation of fixing to access causal parameters. And I'm going to investigate how to use.
Hi, Rodrigo.
Yes.
Sorry for interrupt. We have some clarification questions.
Yes.
Someone asked if you write does not affect the variables. Do you mean you do not fix the other variables, or do you mean you do not intervene in their distribution?
Yes, I think I do not. Well, both of them. When I'm fixing t, I'm only fixing up the variable t. The other variables do not change, besides through the equation that the inputs that are fixed. For instance, fixing t.
Thank you.
Fixing t will not change the distribution of z and v, but fixing t will change the distribution of its descendant in the case of y.
Okay. Thank you.
Oh, I'm going to take a look in the question right now. Thank you for pointing out. Okay, so I'm going to talk about fixing that simply can use the structure equations. I'm going to talk about a little bit about the dual operator and the hypothetical model. So the fix again, I'm just going to fix the inputs of an outcome that we seek to investigate. The dual operator, it uses a different notion of fixing in the following sense that instead of fixing only the inputs of the variable, it's going to completely shut down the variable t in the structure equations. And in the opposite realm, you have this hypothetical model that instead of extracting a variable t to the model, it's going to actually include a hypothetical variable that I'm going to call t tilde that replaces the t inputs in the causal links that we seek to investigate. These three notions are easy to see in this slide here. So the standard method of fixing is the following. I do have the model that generates the data, which y is a function of t, v, and epsilon. And now I'm describing three models that are sort of modifications of the previous, of the model that actually generates the data. In the first one, I'm using the concept of fixing that I say yt is actually fy of little t, v, and epsilon y. The second one, I'm using the concept of the do, the operator do of Perl. And in simple terms, the do it sets the variable t to little t and exclude the t itself to the model. And then I have the hypothetical model that creates a new variable. That's a random variable t tilde. This random variable t tilde is a function of its own error term, so it's an external variable. It does not is a variable that is not a function of the variables in the system. And these are the 3 DAGs of each one of the models. See, these little details of how you are going to implement the concept of thinking, they're pretty much the same. They achieve the same goal, which is the hypothetical manipulation of the input, cause, and an outcome. But surprisingly, they have a very different. They are associated with very different tools for you that you can use to manipulate causal inquiries. And they also associated with different local Markov conditions. When you define the models in this fashion, you do have they imply different independent relationship between the variables, and also generate they also generate a different factorization of the models of the random variables. If you're going to use fixing, imagine that you would like to show that control for the unobservable V actually identify the cause effect of Y little t. And to do so, one way to do this, is simply use, I'm going to use PR for the probability in the model that we fix t. And the method to do this is just to use the equations that define fixing and change the YT until you can show that the probability of the counterfactual outcome is going to be equal to the probability of the Y condition B and T in the empirical model. There's a question here: is structural model different from structural equation modeling? Well, the structural equation model, I think that's a term usually can be using in psychology. So yeah, by structural model, they just say that's a system of equations, autonomous equations that link variables and define causal relationship between them. Now let me go over the hypothetical model. The hypothetical model is just a different way of thinking of get this idea of thinking, of fixing. So I have the empirical model, that's the model that generates the data, and then I have the hypothetical model. In the hypothetical model, I simply create a new random variable, t tilde, and this new random variable takes the place of the input of t on y. For instance, I break the cause effect of t on y, then t tilde affects y. And in this new model here, the hypothetical model, it is easy to show that the expected value of the counterfactual outcome using fixing is going to be simply statistical conditioning. So it solves this issue of fixing not well defined in statistics. However, it creates another problem. How I'm going to identify cause effects? Well, to identify cause effects, I need a rule to connect the empirical model with the hypothetical model. And it turns out that in other papers, we show that we only need 2 rules that connect these 2 models. And these 2 rules are, they use a condition-dependent relationship. So Y statistically depend of T, condition T tilde in W being any set of variables in the hypothetical model. If this independence condition holds, then I can equate the probability in the hypothetical model with the probability of the empirical model. So I can equate this distribution. I can connect these 2 models. And the other rule I use it based on a variable y, the statistic depend of t tilde, the hypothetical variable, condition T and W. And when either of these 2 condition holds, then I can equate the hypothetical model with the empirical model. So for instance, to show that we can indeed access cause effects of the T on Y by controlling of V, we just have to go in the hypothetical model of the IV model and check that Y is statistically independent of T condition T tilde and V, and then use one of the rules that gives the probability of Y condition T tilde is equal to T. Again, this is a cause effect because I'm actually doing a hypothetical model that has this property that be exogenous, so I can manipulate this, and by manipulating it, I get the cause effect of T and Y. Turns out to be equal to the probability in the empirical model of the condition in T and P. And then you have the do calculus. The do calculus is a quite interesting set of tools, and to show that you can condition on V, you're actually going to get the cause effect of T and Y. You're going to use this DAG type of techniques. And indeed, to show that YT is dependent of the condition V, we actually have to show in the DAG nomenclature that V separates Y and T in the DAG GT, which is the DAG that gets rid of the error that goes from T to Y. And to do this, you have to understand the separation criteria, and then check if the criteria applies to the specific DAG, and when the criteria applies to the vector criteria, you have the result that the expected value of Y, when you do T is equal to little t, is going to be the expected value of Y, condition T in P. Okay. Now, the language of potential outcomes is it's a quite different method to examine causality. It is the key feature here is that it's a very simple method that does not use structure equation to describe causal models. Instead, the language of potential outcome avoids the structure equation and already describe causal models using condition-dependent relationships among potential outcomes, and especially of observed variables. So here is our IV model that we use as an example. So I have the structure equation, the DAG, and the local Markov condition. The representation of this model using the language of potential outcome is based on three assumptions. One is the exclusion restriction, that says that YTZ is equal to YTZ prime. So this is pretty much saying that, hey, I do not have a causal link between Z and Y directly. And then you have the exogenate condition that says that Z is an exogenous variable, and also have the ideal relevance. T is not dependent on Z. That means that Z causes T. So it's a very parsimonious way to define a causal model. There are many benefits of the language of potential outcome. It is quite intuitive. It's easier to interpret, and often the assumptions are easy to communicate. And there is also a sense that because you're not using structure equations, you're using fewer assumptions that the model is specified causal model uses structure equations. Well, that is not actually correct, because you can use both language of potential outcomes and structure equations to define the same causal model, and based on exactly the same equations. Okay. And the language of potential outcome is by far the most popular causal framework by economists because of its simplicity, because it goes direct to the point. Now, the main drawback of the language of potential outcome is that the causal relationships, they do not use structure equations, so the causal relationship among the variables are only implicitly defined. And this creates, well, the method is very useful when you're dealing with models that are sort of simple, like RCT, matching, and IV models. But it becomes really cumbersome to use when you're dealing with causal investigations that are more complex than that. I'm going to give some examples to this fact. So, for instance, a very famous causal assumptions in economics is so is there a role for models which combine structural models and LPO, such as single word intervention graphs and other? Well, here both structural equation and LPO in this setup are describing causal models. So in this case here, you use one or another. But it is true that many papers actually have a mix and match both models, which in my opinion, it makes the interpretation, the understanding of what the research is trying to say more complex. So the matching assumption is that Y, the counterfactual outcome, statistically independent of the treatment T condition on X. And again, that's a matching assumption that says that, hey, T becomes exogenous with a condition on pre-programmed variable X. And these assumptions, when you do not put in a context of a causal model, it can lead to the notion that you should condition on the richest possible set of pretreatment variables X. And this assumption is wrong, but in the context of the potential outcomes model, it's quite hard to see why it's wrong. For instance, when you switch to a model that actually determines explicitly shows the causal link between the variables, you can cook up a causal model such as this one here, in which X is a pre-programmed variable and K is a post-intervention or post-intervention variables. And in this model here, it turns out that the YT, the counterfactual outcome, is not independent of the treatment tree condition on pre-programmed variable X, but it becomes statistically independent of T when you condition to a variable that occurs after the treatment K. So another drawback of the language of potential outcome is that sometimes you would like to investigate, for instance, the validity of the instrument condition on variables or some variables W that are also pre-programmed variables. And it's quite hard for you to think about what type of causal links still make still generate a valid instrument without actually laying down the causal assumptions behind the variable on using these independence conditions of the language of potential outcome. For instance, this causal model here, it is true that the YT is statistically independent of Z condition on W. Finally, the language of potential outcome. Again, language of potential outcome is super useful because it's simple and goes direct to the point when you have a model that can be fully that fits well and lays down all the causal links that you need to examine a model. When you would like to investigate further the model, then I suggest you actually go and use structure equations. Here I'm putting an example of two models that are equivalent models, IV models, that one uses the language of potential outcome. I use the average relevance, the exclusion restriction, and the exogenate that I used before. And this model with only these three assumptions not identified. Then I use the monotonicity, very famous assumption of Ibis and Engels 1994, that says that when Z changed from Z to Z prime, all the treatment across all A agents go to the same direction. Okay. Now, this model can be equivalently represented by a structure model in which you define a function Y, outcome Y, as a function of T and U. U is an unobserved variable, and you have the separability assumption, in which the treatment T is an indicator of that's the propensity score of the treatment condition Z, greater than equal to U. Again, U is an unobserved variable that is statistically independent of Z. Well, these two models are equivalent in terms of its causality, but they vary in terms of what you can do with the model. And the key feature here is that the language of potential outcome is way more intuitive than the model that uses separability, but the language of potential outcome does not use the unobserved variable U. And by doing so, the model that uses structure equation allows you to work to have more power of investigation. For instance, with monotonicity, you can compute late, which is the causal effect for the compliers. And with separability, you can compute the marginal treatment effect, which is the expected value of Y1 minus Y0 conditioned on the unobserved variable U. Okay, why the marginal treatment effect is useful? Because the marginal treatment effect, with the marginal treatment effect, I can extend the theory further and express a range of cause effects as a weighted average of the marginal treatment effect. For instance, here put average treatment effect, the treatment, the treatment, the untreated, and so on. Each of these parameters can be written as the marginal treatment effect, multiply a weighting scheme. So weighting scheme has a specific formula based on CDF of the propensity score. And the key feature here is that by introducing the variable u, it allows me to investigate more and create an interesting piece of theory, just because I'm using a different framework to characterize the causal model. Now that's the last part of the talk. I know that I'm almost going over my 45 minutes, and I'm going to talk about complex causal models. So I'm going to explore a little bit of the benefits of a hypothetical model. The key idea of the hypothetical model is that it formalizes the idea of the external variation of the treatment T proposed by Fritsch and Havel. Again, we have the empirical model. We distinguish the empirical model that generates the data with the hypothetical model that includes this hypothetical variable T tilde that replaces the T inputs. And the identification is based on the two rules that connect both the empirical model and the hypothetical model. For you to use this framework first, this additional structure is only interesting for you to use if you have a model that's complex enough. If you have a simple model that can be expressed by language of potential outcome, I would use language of potential outcome. If the model can be manipulated very well by structure equation, you use the structure equation. And the language of potential model, the hypothetical model, is especially useful for you to investigate models that are a little bit more complex. And the rules of engagement is that I define the empirical model, and from that I create a hypothetical model. For the hypothetical model, I can use local Markov conditions, graphite axioms, and so on to generate independence relationship between the variables. And then my goal is to express the probability of y condition T tilde defined in the hypothetical model as an expression that uses probability in the empirical model. And to do so, I need to seek for independence conditions that are the type of y is independent of the tilde condition T and some group of variables, and y is dependent of T condition T tilde and another group of variables. Let me give you an example. And the example here is the famous front door model of Pearl. Due to time, this is the front door model of Pearl. Then you have the unobserved variable V that causes T, the T causes mediation M, and M causes Y, and this model is identified. The hypothetical model associated with this, I just break the link between T and M and create a hypothetical variable T tilde that affects M. The models have different, they imply different statistical independence conditions. And in the statistical independent condition, I seek conditions that are of the type of Y, statistically independent of T, condition in condition T, or vice versa. And I have these three ones here: Y statistically dependent of T tilde, condition M and T; M statistically dependent of T, condition T tilde; and also T tilde statistically dependent of T. This will always happen in this type of models. Now look, I would like to give a sense of how easy it is to use this methodology, because the key feature is for you to go from Y until T. And to do so, we are going to use this statistical dependence condition. So I start with Y, the statistically dependent of T tilde and T, and then you flip. It's also condition M. Then I got this M here. It turns out that M statistically independent of T, condition T tilde. And we also always going to have the T statistically dependent of T tilde, condition T. With the string dependent condition, I can equate the probability in the hypothetical model with the probability in the empirical model. And then these equations are going to be quite useful. Why? Because I can do a factorization of Y condition T tilde, and I'm simply going to do the summation of the probability of Y, and I start condition on M, T and T tilde. Then I do the probability of M, condition T, T tilde. Then it goes to the probability of T and T tilde. When I have these probabilities here, they are all high probability in the hypothetical model, but I can use the equation that links hypothetical with empirical model to equate this all to the probabilities in the empirical model. And whenever I can do this, I have an identification, because I can express a causal parameter, that's the Y condition T tilde, as a summation of the multiplication of probabilities that are all in the empirical model. So that's the identification structure that is used. Now, so how does it differ from the do calculus in many aspects? First thing, the do calculus is a complete method, very interesting method that gets any DAG and examines if the DAG generates a cause effect that's identified or not. If it is, it gives an identification equation. So the method that uses the hypothetical model differ a lot with the methodology used than the do calculus. In the case of do calculus, it has these three rules that combine the three DAG rules that combine graphs, condition dependence probability, and probability equality. But one interesting feature that I saw when investigating these causal methods is that the do calculus in the hypothetical model can generate equivalent equations that identify cause effects, but they can be very, very different one from another. I'm going to give some little examples, about 3 examples, just to exemplify this feature, and then I'm done. Look, these are 2. This is one famous DAG in the literature of inference in computer science, and the key idea is that you have T that's observed, you have mediation 1, 2, and 3, and have an outcome Y, and you have a structure here of unobserved error terms that make them all endogenous. And the hypothetical model associated with this empirical model is the one that, again, I break the causal link between T and M and create the hypothetical model T tilde that affects M1 and so on. Within this hypothetical model, I can retrieve these 5 statistically dependent conditions. Again, you start with Y, and then you condition a bunch of variables in 3, and 2, and 1. Then it turns out that M3 is also independent of T and T tilde. Observe that now I flip the T and T tilde, condition M2, then have M2, condition T tilde and T, and so on, until I reach T. And if I have this structure of dependent condition that breeds Y to T, then it's easy to get the identification equation. So the cause effect of T and Y is going to be, in the hypothetical model, is going to be the expectation of probability of Y condition T tilde. And I can write this using factorization of the probability by Y condition the M's, and then M2 and 3, M2 and 1, and so on. And then I use these independent conditions to equate each one of these probabilities to the probabilities on the empirical model. And when you do so, I get identification. One interesting feature that I'm always going to have this alternate pattern, that here I have a summation that is in T tilde, and I'm fixing in T. And I have an alternation of T tilde, T, T tilde, T, T tilde. One very interesting fact, at least for me, is that if you apply the do calculus, you have this equation here of the identification, and it's quite striking for me that these 2 equations are equivalent, and indeed they are. That's another causal model that's used in this literature. So we are interested in the cause effect of T and Y, and this cause effect is known to be identified. Again, in this model here, I generate these independent conditions by applying methods of local Markov condition graphite axioms. And again, I have this bridge between Y and T. So with these independent conditions, I can express the probability in the hypothetical model, Y condition tilde, as a summation of this sequence of probabilities in the hypothetical model, and then equate each one of these probabilities to the probabilities of the empirical model, and I obtain identification of the cause effect. The equation using do calculus is that one here, and again, these 2 equations are equivalent. finally, I have this causal model 3, which is a model that's used quite famous model in this literature. So here in this model, we have these double arrows that create a correlation between the variables.
Rodrigo, sorry to interrupt. I appreciate if you could wrap it up in a minute so that Ilya would have enough time to discuss
Yes,
as
one
well.
minute. In this case, same thing in this model here, you have the hypothetical model. It turns out that this is the dependency structure that you have that generates in the hypothetical model. Same old. I get the hypothetical model with the probability of hypothetical model. I can equate each one of them to a probability of the empirical model. And in doing so, I have identification. And that's the equation that I obtain. And that's the equation of the two calculus. And again, these two equations are equivalent. That's it. Wrap up. Thank you very much for asking me. And let's go to Ilya.
Thank you so much, Rodrigo, for your talk. And there are several clarifying questions, but we can leave them to the end and switch to Ilya for his discussions. Ilya, please share your screen.
That's good idea.
I think you will have to stop sharing first.
Okay, yeah. Thank
That's it.
Great.
Let's see. Okay. Great. First things first, can everybody hear me okay?
Yes.
Okay, great. Excellent. Thank you so much for inviting me to discuss this very interesting talk and paper, I guess. It's always a pleasure to come hang out at OCIS. So I'm going to discuss both the talk and the paper, although not everything in the paper appeared in the talk. And so this is my summary of the version of the talk that I saw was slightly earlier than the one that ended up being presented, but hopefully it will be consistent. So there is a number of points I wanted to address, and here they are listed in the slide. Causalities in the mind is a big idea in the paper and in the talk. There is this big idea of delineating clearly causal and statistical issues, discussion of potential outcomes and structural causal models, and the critique of these things, and the discussion of their potential equivalence. There's also kind of a call to cite more econometrics causal stuff, which is definitely a great idea. There's also a critique of the dual calculus in the paper, and discussing of fixing versus interventions, lack of perceived lack of ability of sort of structured equation approaches for dealing with cyclic models, and using the Roy model as a running example. So I have some questions and comments in general before I turn to specific things. First is this causalities in the mind idea. Let's say I don't subscribe to that. Let's say I believe causality is a fundamental aspect of reality, physical reality. So what would it actually change that belief of mine for the practical business of doing causal inference, I wonder, if anything? I mean, this is philosophy, right? So I'm just curious what the actual ramifications are for how we should approach problems. Okay. The other comment I wanted to make is some of the critiques in the paper are probably a little bit out of date in 2024, which is supposed not surprising because they're talking about papers from the 90s a lot of the time. Of course, I should say that the causal community is very interdisciplinary. There are all sorts of interdisciplinary folks on this very Zoom call, in fact, which is great, that we're able to find some unifying common ground despite the differences kind of in funding mechanisms and publication models. And I think historically there's been a lot of mileage in understanding many paradigms in causal inference and synthesizing ideas, and hopefully I'll talk more about that. And certainly I agree that we should cite each other and build on each other's work. I hope that continues and we're not siloed as much as maybe we have been in the past. Okay, so first, delineating causal and statistical concepts. So this is something that many other researchers like to talk about. So Pearl makes a big thing of this, and I sort of like in his talks and in his book. I certainly agree with this for pedagogical reasons, because basically people confuse these estimation identification all the time in practice, and they shouldn't. However, I will also, in the interest of some fun, I will express an unpopular contrarian opinion here, which is that sometimes it's helpful to view causal and statistical concepts in a kind of unified way. if you know what you're doing and you get the right answer, right? So it's kind of like a habit of mind to think of them as distinct or to think of them as unified. And sometimes it might be useful to adopt one habit or the other, right? So for example, the missing data view in causal inference I found quite helpful. And in that view, there is a full data distribution on counterfactuals, and it's coarsened by some version of consistency to yield the observed data distribution on the factuals. And typically, you want to invert this coarsening to get some full data parameter from the observed data. That would be the identification part. And the reason this is a unified view is the causal model is just a set of distributions, just happen to be partly unobserved. And the statistical model is, again, a set of distributions, which happens to be observed. And there's lots of benefits for thinking about both of these objects as the same kind of object for doing math, for getting results out. So for example, possibly people on the Zoom call, have done some operator theory in missing data for getting influence functions. And I think it's very crucial to think about the full data and observed data as just coming from two different models, basically. It is still the case that identification and estimation are still fundamentally different things. It's inversion of coarsening versus, solving equations or doing targeted learning. But, I think it's just a style you can adopt sometimes for some intellectual benefit. Okay, so in the talk, there is this line which I thought was kind of interesting, which is potential outcomes structural causal models are causally equivalent but different in their investigative power. My response to that is, what exactly does that mean? If things are equivalent, they're equivalent. If they're not equivalent, they're not equivalent. So I didn't quite get the sense from the talk or the slides what that meant. Maybe sometimes what Pearl likes to say is graphs are easier to use for sort of evolutionary reasons because we got a lot of vision processing in our brain. But I think there should be a way to go back and forth. If we take this idea of equivalence seriously, right? And in fact, people have done this, and so I'll talk a little bit more about this below. So you've mentioned SWIG, so I'll talk about SWIGs a little bit as one attempt to bridge this gap. I'll also make a kind of a sociology comment, which is that typically people who use potential outcomes for a living tend not to read the graph literature, unfortunately. And I think the opposite is, but the converse isn't true. Graph people tend to read potential outcomes literature, perhaps because there's so much of it there. And I think everybody should read everything, basically. The other point I wanted to make is the world of graph methods for causal inference is larger than the structural causal model. Structural causal model is something Pearl came up with, and a lot of people are using, but there are other things that make different sorts of assumptions. And this is sort of related to the idea that if you have a graph, you don't necessarily specify a causal model. There are many causal models. Okay. The critique of PO, some of what I took away from this is it's difficult to assess independence relations. There are no structural equations, and the properties are independencies or Markov properties. And of course, if you learn about single world intervention graphs, you will see that you can formulate potential outcome models using graphs, in which case you could use the full power of deseparation to assess things just fine. And if potential outcomes and structural models, structural causal models are equivalent, we should be able to formulate potential outcome model with structural equations and vice versa. And people have indeed done that. It's not very difficult to do. As far as other properties, there's nothing is preventing people from augmenting potential outcome models with other stuff like monotonicity and so on. And of course, lots of people have done this already. Okay, now this is more from the paper. The version of the paper that I've read, which may be out of date, claims that manipulations in the dual calculus are within the empirical model, so within the observed data distribution, which is sometimes how Pearl describes it. Like you start with a normal structural equation, you replace it by a constant. The second critique is there's no distinction between observed and intervened on versions of treatment. And finally, you can only represent non-parametric like Markov restrictions implied by the DAG. And what about these other things like monotonicity, linearity, rank preservation, and so on? And my response is, I don't want to speak for Pearl. I would guess that Pearl would probably disagree with one in the sense that to Pearl, the empirical model, what's called the empirical model in the paper is not the fundamental object. The structural equation model is the fundamental object. So I don't really see that as a disadvantage, at least the way people understand manipulations in an SCM. I think the critique too is right on the money. I think it is true that the original do notation had some difficulties representing multiple treatment versions. And this comes up for things like effective treatment untreated or mediation problems being difficult to express with the do notation. If you notice in Pearl's causality book, He doesn't actually represent mediation with do notation, precisely for this reason. Although there have been recent extensions that sort of changed that, and I'll talk about some of them below. As far as representing non-parametric other restrictions than non-parametric Markov ones, as in computer science, we would say that's a feature, not a bug. It's because there is no general way to incorporate these kinds of restrictions into a general reasoning system. So Rodrigo mentioned that do calculus is complete, and so it's very difficult to get complete reasoning systems. But of course, nothing is to stop us from incorporating them on top of the graph. And again, people have done this all the time. I have my own critiques of the do calculus I thought I should mention, since we're on the subject. This is the do calculus for folks who are not familiar. This is in the paper also. I'm not going to describe it. It's just rules that allow you to manipulate do's and conditioning based on path separation relations in certain manipulated or mutilated graphs. You know, the problem with the do calculus, of course, is what we call a declarative algorithm in computer science. It tells you what is true, but it doesn't tell you how to find the proof. You have to look for it. And that's obnoxious if you have a very large graph and a very large problem, unless you know exactly how those proofs go. Why is it that the do calculus uses those specific graphs? It's not completely clear. Pearl talks about mutilation, but some of the mutilated graphs in these rules are a little weird. They're not the usual ones, which is interesting. Rule 3 is particularly weird and difficult to explain to people, speaking as somebody who tried to explain them to people. And what exactly is the do calculus like conceptually, other than this famous reasoning system that Pearl came up with in 1995? And what are the connections to the potential outcomes? Here are some SWIGs. The idea with SWIGs is regular DAGs representing the empirical model, as the econometricians would say, factorize as a product of terms of a variable given its parents. And you can also similarly factorize a counterfactual distribution in a very similar way and come up with a graph that corresponds to this factorization. Here's an example graph called the single world intervention graph below. The way it's obtained is you basically split the treatment like a watermelon, and you relabel downstream variables of the treatment, of the fixed version of the treatment as counterfactuals. So it's very important that you're able to put counterfactuals on the graph. Notice that in the SWIG, you can have two versions of the treatment, the normal version, the natural version, and the intervened on version. I should also say that seems to be a very close connection between SWIGs and the kind of graphs that appeared in the paper with Heckman. It's probably worth investigating. SWIGs have been out for quite a while, since 2013, I want to say. So anyways, the nice thing about SWIGs is they mimic, they allow you to use the full power of the Markov property of statistical DAGs, which are based on deseparation. Here's a quick deseparation example here. H and M are deseparated given A, and therefore in any distribution that factorizes like this graph, you have a corresponding independence. And so similarly in SWIGs, you can talk about deseparation in these split kinds of graphs, except that you can also discuss being separated from a fixed variable. So for example, the counterfactual Y of parentheses A and M is independent of the fixed A. It's kind of like an exclusion restriction, if you like. And you can see that because there is no path connecting these two vertices. The important thing about SWIGs is they allow us to discuss the observed and intervened versions of the treatment simultaneously, and they allow us to discuss things like ignorability and other kinds of causal assumptions that people use that look like Markov restrictions. And you can use SWIGs to reformulate the do calculus in terms of potential outcomes. Here are the three versions of those rules. You will notice that rule 3 is significantly easier, is just causal irrelevant. Basically, it's exclusion restrictions in the graph. Turns out that that's without loss of generality, the simplification. You can also, so first it ties together potential outcomes in the do calculus, and second, it just kind of clarifies what it is that the do calculus really is. It's just, if you reformulate it in this way, it's just a useful fragment of the global Markov property on a SWIG. And that's all that you're really using when you use do calculus. Or po calculus, if you want to rephrase it this way. So here's an example derivation. We have lots of other examples in the paper, and in this derivation, we use the original graph and various kind of SWIGs that correspond to different splitting operations. And of course, we get the right answer in the end, and which is not surprising because this reformulation is still complete. I should also mention, people have addressed this critique of do calculus as a declarative algorithm. There are now explicit algorithms that will identify any identifiable effect in a graph. This is known as the ID algorithm. I'm not going to go through it because I don't have time. It's like a whole talk. But here's a crazy DAG example where we want to know the effect of A and Y, and it happens to be identified. And it happens to be identified by this weird formula that doesn't look like a typical thing you would get. People will ask, in fact, there was a question in the chat, something along the lines of, well, do these complicated graphs come up for you? And the answer is maybe not. This graph I came up with as an artificial example is just to illustrate that weird identification is allowed sometimes. But the thing is, you kind of need a general reasoning system to be able to address anything that might come up and develop extensions that would potentially be applicable. Similarly to how we have a general reasoning system called piano arithmetic for all integers, even if in practice we don't work with integers larger than 1 million for the most part, right? So it's the same kind of thing. You need a general reasoning system. So to conclude, I love this quote by Wittgenstein. I like to think about causal inference in accordance with this quote. The limits of my language are the limits of my mind. All I know is what I have words for. So I think there's lots of important insights into causal inference from lots of communities, which includes, of course, econometrics and computer science and philosophy, statistics, public health, social science, and so on. Very smart people in lots of these areas use different formalisms, use different languages. And I think it is advocating a single paradigm approach to causal inference, whether it be potential outcomes or DAGs or the Heckman model or whatever it is inherently intellectually impoverishing, okay? So the way I think about these things is there are kind of styles of causal kung fu, if you like. And the more styles you know, the more likely you are, it expands the language that you're able to speak, first with others, and second, just to think about your problems. So the more styles of kung fu you know, the more likely you are to realize a particular style can address a methodological difficulty you are facing. And in addition, a very welcome recent trend is an intellectual synthesis of multiple approaches to causal inference, such as graphical and potential outcomes-based approaches by the Swig paper and subsequent follow-ups. And I hope that this trend continues, and I hope that it incorporates more insights from econometrics to the intellectual enrichment of all of us. Thank you, Rodrigo, for presenting. This was great. And here are the references I've used. And thank you for listening.
Thank you very much, Ilya, for your interesting points. We are running out of time, but I would love to give Rodrigo some time, a few minutes maybe, to respond if you should see. Rodrigo.
Well, I completely agree with Ilya. Indeed, well, again, I like causality. I especially kind of like the methods of the calculus and how other people think about causality. And I learn a lot from this literature. And I cannot agree more that knowing kind of how other people actually think, it makes you much more keen to understand the relationship and develop methods that suit your problem in a specific way. For instance, in the point of I like the approach that use more complicated methods and more complicated tools only if they actually become necessary to actually address a problem. If the problem is very simple, just use kind of the simplest method that you can. And indeed, kind of a great presentation and very interesting topics for me to study and check. Very nice.
Thank you, Rodrigo. Thanks for your interesting talk, and thanks you again, Ilya, for your discussion points. I apologize to the attendees who had some clarifying questions, but I think all the questions will be sent to Rodrigo directly. And I'll just wrap up by I hope you see my screen, by letting you know that next week we will have Wang Miao from Peking University, and hope to see you all there.